Let's do a quick warm-up, both as a review and because it will be useful in just a moment. Part one, if f of x comma y equals x cubed times y, what is the gradient of f? And then part two, take the vector with components 4 and 1, a two-dimensional vector, normalize this vector v, and then call the normalized vector u. And neither part is too bad, right? So the first part, gradient, we get a vector where the components are the partial of f with respect to x and the partial derivative of f with respect to y. So we have a 3x squared y comma x cubed. And then to take the vector v, which is 4 comma 1, and normalize it, we compute that the magnitude of this vector is root 17, so we just need to multiply by 1 over root 17 to the vector, and so we really end up with 4 over root 17 comma 1 over root 17. I'm really not worried about doing a rationalizing of the denominator here. Now, just as a reminder, if you're still perhaps concerned that this is working correctly, you should verify directly that this vector 4 over root 17 comma 1 over root 17 has magnitude 1 using the formula. That is, if you simplify the arithmetic here, you should get a 1. And really, the point is to convince yourself that dividing by the magnitude always produces a unit vector. And if that's really the case, in a similar way, if you start with a vector w, then 2w is twice as long as w was, and 1/2 w is half as long as w was. And that's really why, if you just keep extending this through, multiplying a vector w by 1 over m produces a vector of length 1 as long as m is the magnitude of the vector w. So previously we had done this with partial derivatives. Given a function f of x comma y, we defined two partial derivatives. There was the partial with respect to x and the partial derivative with respect to y. And if we just picture what's going on using just the input space of x and y only, right? So this is just a picture of the input dimensions and does not include the z-axis here. Then the partial derivative of f with respect to x at the point x naught y naught asks how does z change as you move in the x direction, while the partial derivative of f with respect to y asks if you start at this point here, how does z change if you keep x constant but you move just the y coordinate. Now what we're going to look at is a thing called the directional derivative. The directional derivative, which we're about to introduce, can answer things like how does z change instantaneously as you move in any direction, such as moving in the direction of the vector 4 comma 1. The definition looks like this. It's a little more complicated than what we've seen earlier with partial derivative. But so I want you to try to process this as funky as it looks. The directional derivative of the function f of x comma y at the point x naught y naught in the direction of the unit vector u1 comma u2 is this. So the notation, first of all, is capital D, and as a subscript you write the unit vector and then mention the function f, and then at the point x naught comma y naught, it is a limit as h approaches 0. And what we do is we actually move a scaled copy of the unit vector. So u1 comma u2, you see, the x direction, or the x component is u sub 1, and so we do h times u sub 1 added to x naught, and we do h times u sub 2, that's the y component of the u vector, added to y naught, and then you subtract from that the original value, the original z value, all divided by h. So I hope this, as funky as it looks, seems similar to some of the other things that we have done. And while that's the definition, we won't go through all of the steps to get there. The definition is, I think, helpful to see what it is we're really trying to get at, but then to actually compute it, it's actually very nice. What you do to compute this directional derivative, instead of doing this limit-based thing, is you take the gradient of the function, evaluate it at the specific input point, x naught, y naught, and then dot product that with the unit vector. That's the direction you want it to travel in. The key thing here is that u must be a unit vector. So let's actually look at a quick example. What is the directional derivative of f of x comma y equals x cubed y at the point -1 comma 6 in the direction 4 comma 1? So I've called the vector here v instead of u because this vector v is not a unit vector. From the warm-up, we had already computed the gradient. Like you see here. We just need to evaluate the gradient at -1 comma 6. So you see this vertical bar and then the specific point. There are a couple other notations, but let's just stick with this right now. The whole point is to take what we see right here, plug in -1 for every x and 6 for every y. You get a thing that looks like this, which happens to simplify to the vector 18 comma -1. All right, so that's this part. We need to now dot this with a unit vector. V is not a unit vector, right? The vector 4, 1 we already saw had magnitude √17, but we had, from the warm-up, we had normalized this, right? So we had already a vector that's in the same direction, but is a normal vector or a unit vector is 4 over √17 comma 1 over √17. And now we take, as we see up here highlighted in red, we should now take the gradient evaluated at the point, so that we have the vector 18, -1, and then the unit vector right here, 4 over √17 comma 1 over √17, we should just dot those together. So here we go, right? So the directional derivative at -1 comma 6, sorry, there's a missing comma here, equals this dot product, and if we just write that out, this will be 71 over √17. So here's the point. Here's an interpretation of what's going on. So starting at the point -1 comma 6, if you start moving in the direction of v or in the direction of u, again, I'm using the word direction here in a very, not in a very technical, I mean, sometimes calculus books say direction vector must be a unit 1 vector, but I just mean if you move in the direction that the vector v points, well, the vector u also points in that direction. So all I'm trying to get at is, since vector v was 4 comma 1, moving in a 4-to-1 ratio of x to y, then the z coordinate changes instantaneously by 71 over √17.